Welcome to Espresso Engineering. I am Steve Ferguson. Join me as I guide you through the test methods of MIL Standard 461F. Today our discussion will be regarding CS101, conducted susceptibility. This is accomplished on power lines according to the MIL standard, and input power leads is the primary problem. Where do these interferences come from? From various places. A lot of equipment have harmonic distortion and just general noise that is left uncontrolled and placed on the power lines as it enters your piece of equipment. This is to determine if the equipment is susceptible. So our limit and discussions think differently from the emission side of the world, where we're looking for a test level, and the pass-fail criteria is, does the unit react to it, react disfavorably? Does the performance degrade beyond its tolerances? So we're going to be applying an interfering voltage to the test article on the power and determine if it is susceptible to that interference. The frequency range is from 30 Hertz for DC powered equipment, or starting at twice the power line frequency. For instance, if the power line is 60 Hertz, the test would start at 120 Hertz, up to 10 kilohertz. The excuse me. The susceptibility signal is measured as a term of voltage. However, there's a secondary limit called the power limit. This is determined by dissipating a particular power following the curve that's in the standard, and at low frequencies this power is 80 watts, into a half-ohm resistor that's used in place of the test article. So we establish a maximum power drive as one limit, and then the test voltage as the primary limit. So our goal is to apply the lesser of the test voltage or the forward power that we determined prior to test using this calibration fixture. So for discussion purposes, let us talk about the calibration. I'm going to kind of demonstrate this or draw it as we go through the discussion. There is a power limit that we described, and that is some forward power, and this happens to be 80 watts. And at the end, at 10 kilohertz, it's 0.09 watts. Now that's not real significant, other than 80 watts is a fairly high wattage, so we start warming things quite a bit. The test circuit is, we're going to have our signal source, our signal generator, tied to a power amplifier, and this goes to our coupling transformer. The secondary of the transformer is connected to the resistor that is set for calibration, and that is 0.5 ohms. This is basically the test circuit used for calibration. We generate a signal and apply power to where we dissipate 80 watts in that resistor. And as the frequency goes up, this breakpoint occurs at 5 kilohertz. And then we start diminishing this. So prior to the testing, we need to have a measurement method here. And what we will do is we'll connect a voltmeter of some sort. And the voltmeter could be various things, an oscilloscope, or whatever we determine to measure, an AC voltmeter, something with the frequency response to let us go to the upper test frequency of 10 kilohertz. So this is a setup that we can generate, we can configure for getting this pre-calibration done. When we do this, we need to record what values we're applying. So at the output of the power amplifier, we need to put a voltmeter of some form to measure what we're applying on the primary circuit. So this becomes our reference point once we have gotten these levels established. Now, our point is to generate this power here. We're trying to measure with a voltmeter, so prior to test, we will calculate those levels that we need to do. For 80 watts and half ohm, we need to have 6.32 volts RMS. Now that will be providing the 80 watt dissipation in the resistor. So let us consider doing that. And we tune through the frequency range and the calibration, verifying the voltmeter settings. When we have to change the levels, we need to take another measurement point so we can record where we are. We're doing a susceptibility test. So now instead of us being below a limit line, we need to be applying the test interference slightly above the limit line. For instance, I will apply during the test someplace just above the line. And when I get out here to where this is decreasing, let me make a little space here. We decrease, and we come out here just past this, we decrease, we step, we decrease, we step, we decrease, we step. And that process goes on until we have all the frequency ranges needed to determine our calibration. This establishes a maximum power. Why do we need that? If the test article happened to be a very low impedance, as in lower than 0.5 ohms, we would try to put more power into this to try to create a voltage across that resistor or the load circuit of the test article. However, we don't get there. We keep increasing the drive power until we develop that or we burn something up in the process. So the goal is the lesser of this pre-calibrated forward power or the test voltage. Okay? So now the calibration process goes on. We will go to the lab in a moment and discuss how this goes on, the calibration process. But fundamentally, generator, this. When we're doing this sweep across the frequencies, a lot of folks will determine I'll take a point here and a point here and not look at the level as they're doing this. They just want to measure the points. The idea is we need to verify that this waveform that we're planning to do interference testing with is sinusoidal in nature. So we'll be monitoring this. We'll also, during the process, look to see if there are fluctuations that cause this thing to decrease or increase, and we'll adjust the forward power to where we're producing the right levels. So just to recap, signal generator output to a power amplifier to the primary of our coupling transformer. The voltmeter will measure what we're applying. Out here, this voltmeter will measure the voltage associated with this power level. When you do this curve, you want to pre-identify these so you know where your points are. In the real world, we're going to use like a spreadsheet or something along that line to calculate these so we know where we're going to be setting things ahead of time, so we can drive this thing properly. But once we get to the end of the test frequency, we will stop this calibration. This calibration is used for multiple places. So we do the calibration just prior to doing a test and then use it on as many lines as we need to. This test is done on the phase lines of the power. Phase, not neutral. A lot of tests will look at using both lines. But when we get into the drawing on the test article configuration, we will understand the difference. Okay? So fundamentally, that is our setup for the test, for the calibration. With that, let me take away this part, and let's take a test article and put it in place. This is the configuration that we use for calibration. These articles are part of our calibrated instrumentation at this point. So now I need to bring in a test article. Well, I have the listen, with primary power. I have an AC power source or a DC power source. What do we have? I come over here with my phase lead and go through the transformer and over to a test article. This becomes my equipment under test, our EUT. So now we have placed this transformer in line with the phase lead of the power. Now we need to measure this item. So we have a voltmeter, an oscilloscope that we connect to the terminal, so we measure the power going into this unit. Measure the test voltage being applied. So this is our connection. Now what's going on is I generate a signal, I create current to flow with that signal through the test article. This test article has some sort of a load circuit that we will be applying through for our total loops. Our power coming in comes through the load circuit back through here to the secondary listen or the current loop. Now this is problematic in some respects. The test article has 60 hertz or some frequency of power unless it's DC. When I have current flowing through this network, this secondary to primary also occurs. So 60 hertz provides feedback back into this circuit. Depending on the impedance and the current draw of the equipment, we may have trouble getting the test article to actually start because this reflected impedance will show a high impedance and prevent current flow in our circuit, so our unit never gets the power to start activity, especially if there's a high inrush current. So we may need to temporarily connect a resistor here to provide the startup current, and then we can switch it out. So you definitely want to get something you can switch in and out. So we have a process of getting this to happen. Also, we have to worry about the power amplifier. When we feed back this power, it creates a voltage across the power amplifier, and the amplifier may think there's damage tolerance, that it's overpowered, overcurrent, so it may turn off to protect. So then the circuit becomes open and we don't operate well. That's a separate subject that we probably will not get into in this video, but it's feedback control. We'll discuss it a little bit more when we get into the testing, but there's some options and they're discussed in the MIL standard related to feedback control. However, we're going to discuss why some of them don't work very well. Now here's a secondary problem. If I look at the listen, I've got a couple of capacitors to my ground system with an inductor. Now that's what's inside this listen. So this inductor presents, as the frequency of this test goes up, the inductor presents a very high reactance. This reactance starts dropping the voltage across the listen here and the listen here. So my goal to get voltage to appear here doesn't happen because all of my voltage drop is in these two circuits. Remember, my loop goes through the whole arrangement and I'm measuring that part. So I need to be able to control that element. The standard calls for putting a 10 microfarad capacitor across those leads. It is absolutely critical that you do that or you're measuring incorrectly. This capacitor provides a short circuit as the frequency increases. So as the listen's impedance is going up, the capacitor impedance is going down. So they cancel each other. The capacitor now acts as a short circuit for this signal and a high impedance for the 60 hertz. So our power loop stays the same, our injection loop alters its path, but allows the voltage to be dropped across the test article, not through the setup circuits or the listen. So now that we have this process ready to go, all we're trying to do is apply an interfering voltage to, assuming we get everything to start up, we apply the interfering voltage. We turn the signal generator on with the power amp, elevate the voltage until we measure the test limit. Now we're talking test limit. This is a forward power limit. A test limit is a similar type line, and there's a couple of them in the standard, and this is, I think it would be greater than 28 volts and equal to or less than 28. I believe those are the two curves that appear. So this voltage is our goal, our test voltage. So we try to measure the test voltage appearing here. If we get to where the pre-calibrated settings were met, then we consider it compliant as long as the test article is behaving. So 2 volt, 2 curves going on. As we go through the process, we'll do more with this. The complexity is we have to monitor 3 things: test voltage, forward power settings, and the performance of the test article when we're doing this. So any one of the 3 can be a set point that we have to evaluate. Let me think for just a moment. As we go through the test frequencies, we're providing this, and when we start doing the actual testing, we start creating the applied voltage. In our data collection, we have a process of the chart showing the limit, and we're applying the voltage points above that limit, and suddenly we can't get there. And that indicates that we have hit this forward power point. So we're creating an applied voltage that follows a curve differently than this. In this region, where we're below the limit, we're assuming that we were applying this pre-calibrated numbers. All this information should be recorded to determine what voltage was being applied no matter where we are. So the reporting should present all this information. This is the applied voltage. The pre-calibration numbers should be available. Let us say that the test article did not behave, that something erroneous happened. Well, we'll say the fan quit running. You know, at some point the ventilation fan stopped operating because of whatever reason. We now need to know what was the threshold of that susceptibility. At what voltage did that circuit stop operating correctly? Now, what stopped operating? Well, if it ceased to run might be a threshold point. Clearly that would indicate a severe problem. However, if you start hearing speed changes, and this should be determined prior to the test in your planning element, what is the susceptibility threshold? What is pass-fail criteria? Without knowing that, you don't know when this test is being accomplished. So pass-fail criteria says if the fan slows, and how do we measure slows? We must have a monitoring system to let us know that the fan is slowing. How about a temperature change for a monitoring circuit? The video goes distorted. At what point do we have pass-fail? And remember, these pass-fail criteria need to be objective, something that's 10% variance in the measurement, some hard number that you can say this is acceptable and this isn't. However, reality takes over. We know that video distortion is a very subjective item. You may be able to see that screen, but your partner may not be able to see the screen and determine what's being presented on the information. How about audio noise? Is the signal-noise ratio makes it unintelligible? Lots of things call for determining pass-fail criteria. Try to establish a point where it's very objective, whether it's yes, no, very solid numbers. Something that's measurable, quantifiable. That should be done in the planning stage before you ever started this. So when we start this process, we know where we're going. We've selected our limit. We go through the process of calibrating. We did that, and now we connect the same equipment in here and do the circuit changing. Now, here's an inherent problem. I've got a very big signal, okay? Because our test article happens to be 115 volts. So now I've got this 115 volt 60 hertz signal that is present on my oscilloscope. I could get to see that, okay? Now I'm trying to apply a very low level, 3 volts, 4 volts, some very low level signal in my test limit on this. So what I see is a very small excursion happening on that 60 hertz. That's the part I need to measure. Now if I've got very high frequencies, as you can kind of indicate there, it's not very difficult. But when I'm at 120 hertz, I'm only getting a small variation. So this item doesn't vary at all. It kind of dips for a moment, and out here it may dip again. But if I'm synchronized 120 on top of 60, I get 2 of my interfering cycles per 1 of the primary power. So the variance across here is an oscillation of this waveform kind of moving up and down slightly. We will see that in the laboratory, because it's very difficult to measure this circuit. There are some filters available. You can look up some elements. There are articles about filtering and things like that for oscilloscope measurements where it doesn't prevent this, because the filter goes into the oscilloscope circuit that takes the 60 hertz out or the primary power out, whatever frequency it is. Okay, we've got this safety problem going on too. And I didn't mention it so far, but now we've got 60 hertz appearing here and here. Now if I've got a grounded neutral, my neutral lead of my power here connects to my oscilloscope body. If that's grounded and the scope is grounded, no issue. However, if this is an isolated power, for instance for Navy applications where they don't use a grounded neutral, or 3-phase power where I'm going to measure between a phase A and a phase C, for example, I have a high voltage appearing on this lead. Well, that lead happens to be the body of the oscilloscope. So if you go up and touch this connector while it's live, my oscilloscope primary power is grounded, so now I've shorted this ground to that. What happens is my probe flashes in a ball of flame, lasts a few milliseconds, the flame's about 7 inches, and your probe burned out. Okay? So we have to put an isolation transformer here to prevent grounding of the oscilloscope to the primary power. Okay? So when we do that, we make this oscilloscope body a live circuit. Well, most of our oscilloscopes have a plastic body, except for that little B and C connector that we use to connect the probe to. So if you touch that or the ground pin on this oscilloscope, you're live. If this is a floating neutral with 480 volts, you're going to get between there and the actual ground, and your body will be the conductor. It is pretty severe shock. So remember, we need to isolate unless we're absolutely sure this is a grounded neutral. So we always just isolate instead of being so sure about it. Okay? We don't want to provide another path for the currents. So typically we put an isolation transformer in place at the oscilloscope to prevent this damage. With that, that's a kind of coverage of CS101 and how we approach the test side of this. We can go to the laboratory and examine this, see what it looks like when we actually do the testing. I almost forgot that we need to talk about this feedback a little bit more because that's a control subject. Let me make some space here to talk about feedback control. This is not a very difficult matter. It's presented in the MIL standard, and we use this. As I have my coupling transformer for my primary circuit, I have this power amp and signal generator. This is the primary circuit we had. I mentioned that feedback presents from 60 hertz coming back across the line into this item. For very high currents, this feedback presents too much power into the, feedback into the power amplifier and causes it to shut down as a protection mode. Now, we can stop this by taking our primary voltage into another transformer. And this transformer is brought from this, except we change the sense lines, so this one, which happens to be that sense, is opposite of that one with the sense winding. So these circuits are now 180 degrees out of phase. We put a dummy load on this circuit for the power, a load of some sort that emulates the test article. So this load circuit is drawing the same current as this load circuit. So effectively what I have on this side, the 60 hertz being fed back, is that waveform. The 60 hertz being fed back on this one is that waveform. So we have a net cancellation. Ends up with 0. This is how it's described in the MIL standard, providing this type circuit. The figures are obviously much more cleaner in the standard. But the idea is that should work. The inherent problem is that assumes that this test article and our load circuit are linear. They don't have distortion. We know that a lot of test articles, switch mode power supplies, things included in the test article present distortion. So if I have a load circuit that's resistive, I have this cancellation waveform of one thing, and I have this waveform for the primary being different. So now they don't cancel. I need that waveform to cancel. So all of this area where the distortion causes the waveform not to be sinusoidal presents a current that's not being canceled. If this is excessive, it will cause the power amplifier to trip. Now, quite frequently you don't notice this. You get started with the test and everything is happy, and 2 or 3 seconds later it suddenly trips because the phase variance has changed ever so slightly to get to the point where this power amplifier shuts down. You'll never get through the test. You have to be able to cancel with the waveform identical to the test article. Okay? Without that cancellation, you don't get there. So the circuit that's in the manual doesn't quite do the trick. When you encounter this kind of element, what do? I can't answer it. I do various things, but planning for it is the key. Understanding the process. That if you plan to have this kind of an event and a backup approach, then you might have a test to go. Quite frequently this requires tailoring of the testing because the standard doesn't quite fit the bill. Tailor the test, come up with an alternate approach, and present that for approval during the planning process. So you understand feedback a little bit better and how the circuit that's described may not be effective for you. Well, we're in the laboratory doing our CS101 pretest calibration. As you can see, I have connected the secondary of the transformer to the half-ohm resistor as prescribed in the standard. The oscilloscope is our measurement source. A measurement instrument is connected to the thing, to the resistor to measure the voltage across the value. We have predetermined what voltage we'll be applying for that 80 watt power dissipation. That's the requirement down at the lower frequencies. And the calculation shows that we need 6.32 volts to be applied at this frequency. Our start frequency is going to be 120 hertz, or twice the power line frequency. We have a 60 hertz test article that we're going to work with. And that's the whole setup, with the exception of I don't have my signal source, and I will plug that in and connect that to the primary of the transformer. And now I basically have all of the instrumentation that I'll be using during the test. The power amplifier, the signal generator, the oscilloscope for measuring, and the transformer. Note that I did not point out a voltmeter for measuring the output. That is built into the instrument. So we have a voltmeter built onto the item. So we'll be monitoring all of those items, recording what the voltmeter setting was when we got the power dissipation that we said we were going to. With that, let me get started. We've set the generator to 120 hertz, our start frequency. And we will say that in our item here. So 128 is the start frequency. I need to go to 6.32 volts. I have the instrument turned on and engaged. So I will be adjusting the output level, noticing that I'm getting a signal on my oscilloscope. The oscilloscope is set to monitor that voltage, and I'm going to adjust to the 6.32 volts that we determined to be required for the 80 watt dissipation with a half ohm. So there's 6.32 volts, actually slightly above, and I want to be slightly above. Remember, I'm doing susceptibility. So there's 6.37 volts. My voltmeter says 13.95. I record that number. I go on to the next frequencies. As long as I can maintain my 6.32 volts while I keep my RMS voltage output steady, I'm good. So now I'm going to adjust the frequency, and I'm going to monitor the oscilloscope for the changing waveform to see that it stays sinusoidal. If I start seeing that it drops below 6.32 volts, I'm going to adjust the level to be higher. I will constantly be adjusting the oscilloscope so I can monitor the signaling going on here. I'm maintaining the 6.32 volts. Notice that I'm not doing much with frequency. I'm not worried about what the frequency is at this point. I'm going to be constantly driving the frequency higher and higher and maintaining my voltage level. Now, this is not uncommon to see a very stable circuit like this. The 6.3 volts, the sinusoidal waveform maintained. I keep adjusting the frequency while I monitor it. I don't see excursions going on the waveform that I'm monitoring, and the RMS voltage output is staying pretty stable. And this continues until I get to a point where it drops below that level. And at this point, I started to drop below 6.32. So my next frequency point of interest would be 766. So at 766, I will be adjusting my output level to raise the applied signal, the dissipated resistor above 6.32. And so I'm going to go up to about 6.4 approximately. Now my voltage level is 14.2. So at 766 hertz, I increase my voltage level for the maximum power to 14.2. Until then, I'd stayed at 13.95. So we keep trapping these points where we have to increase the level in order to maintain the power dissipation. We continue the frequency change, monitoring for a sinusoidal wave and above 6.32 volts. I'm maintaining this. 6.32 is still being maintained. I've got to 1 kilohertz. I will need to change ranges. Let me go ahead and record 1 kilohertz. 1 kilohertz, and I still have 14.2. And at this point, I'm going to change bands of my signal generator and adjust the frequency back to 1 kilohertz to resume at that point. I still have my 6.32 volts with the right level at 14.2, so we're going to continue the frequency sweep until we lose below 6.32. And there's the point where I did that. So my next frequency point of interest is 1.12 kilohertz, and I have to increase the voltage now to produce greater than 6.32, and I usually go to 6.4 roughly, and now I'm maintaining a 14.6. This process continues until we get all of the frequency range accomplished. We've recorded all of our numbers. Now note, when we get to 5 kilohertz, the power limit starts taking a curve to where it starts decreasing. So we'll have to be much more attentive to how far we are above the level. So let us realize that now I have these points already determined. Once I get this complete set of data for the pre-calibration, I know what the voltmeter setting is for the maximum power. With this, once we've recorded all these numbers, we're ready to proceed with the testing. So let us go towards the testing at this point. Now that we have our configuration wired for testing, our test article would be this power unit and its load circuit. We've simulated one here just for demonstration purposes. And this is wired back to the system. Now I'm doing this preliminary check before I apply power here to make sure everything is right. I have the terminals exposed. I have the oscilloscope wired to the item to monitor the applied voltage. I have the neutral leg going to my listen, and the listen also connected to the return of the feed-through capacitor. I have the positive side, or the phase lead, wired to my coupling transformer, from the coupling transformer to the capacitor. And remember, the capacitor is parallel, but since this is a feed-through capacitor, we go straight through for the one side. And this comes back to the phase side of my listen. The wiring appears intact. I have no items touching, so I'm ready to apply power to this unit. At this point, I will plug in the primary, and we should be ready to operate. Notice that immediately before I start applying my interfering signal, I have this gigantic signal on my oscilloscope. Let's get to the point where we can actually measure this, and you'll find that this is a 60 Hertz primary power. When we were doing the calibration, we were using the measurement circuits here to determine what our applied voltage is. Obviously, that's not going to work now because it's going to keep measuring the 120 volts being applied. So that's going to be my primary problem, is I have to measure my signal in the presence of that signal. When I go to the calculations, this is a curve 1 test limit. I've converted that into a volts peak to peak because I can't measure RMS, as we discussed. I need 17.8 volts peak to peak, but I don't exceed the pre-calibrated forward power, which was 13.9 volts out of my signal generator. So when we're ready to do this test and it's operating, everything is checked out, we're monitoring the unit for its proper operation to make sure that we can see all the elements. For a demonstration here, I'm not going to do that, but in the real world, I'm going to be seeing if this unit makes any kind of susceptibility indications, which had to be predetermined. What's the pass-fail criteria? So with that, I'm ready to apply power, and I'm set at 120 Hertz, and I start increasing the voltage. And I'm monitoring the EUT for performance, as well as I'm trying to see if there's a signal going on the oscilloscope. And I'm starting to see this oscilloscope. At this point, I can see that I'm having a lot of trouble trying to see my applied voltage. This is occurring by that you can see the peak amplitude of this waveform varying ever so slowly. And that is what the interfering signal is doing. I'm going to turn the output level down again just to show you on the oscilloscope that that disappears, that movement, and then becomes a very stable signal. I increase the level until I get the excursions to be 17 volts, 17.8 peak to peak. We're on 50 volts per division, so I'm going to actually position the waveform to where it's not very visible to me so I can get better resolution. I'm at 20 volts per division. So 17.8 volts would be approximately 1 division peak-to-peak excursion. So I keep adjusting this till I see that waveform varying by that amount. But I don't want to exceed my 13.9 volts from the voltmeter. At this point, I can see that the waveform is varying 17.8 from its low point to the high point. Now this particular method of using this is very deceiving to the eye. Your eye wants to keep integrating this where it moves along. So you have to pick a vertical point that makes for better measurements. So I'll tend to adjust horizontally until I get the waveform on a fixed line that I can see the peak going up and down. And you see it's almost hitting this division and that division, which is 20 volts. So I have the peak-to-peak exceeding the 17.85, and I do not have my forward power limit met. I am below the 13.9 we had established. The test article is everything is operating correctly. I record the measurements that I applied greater than 17.8, but for graph purposes I'm going to put down here 18 volts as a nominal, and the voltmeter was at 11.63. Do I need that number? No. I do not need it. I record it just simply for complete test record. Then I go on, and the frequencies have been preset, but basically we need to sweep the signal. We're constantly adjusting the frequency, maintaining that peak excursion. As I go up past 120 hertz, we can see that at 125, now I'm seeing a much more exaggerated excursion on the oscilloscope. It's very much faster. What's the reference to that? 120 was exactly 2 times the 60, that's our primary power. 125 doesn't do that. So I'm still seeing the excursions. I position it to make sure that I am going peak to peak with those items, and I am. So I can adjust the frequency to where it's a little smoother or much more dramatic. The idea is I need to measure the interfering signal, the voltage being applied here in the presence of all these items. Now there are some oscilloscope filters available that will take 60 hertz out. It also removes some of the interfering signal, so it requires calibration. But for our purposes, we don't have it available, so we're just going to monitor this. I am seeing excursions in my eye, and I'm the one that's doing it, and when you're doing it, you'll have to determine, am I seeing a peak-to-peak excursion in excess of 17.85? And if you don't think you are, you're going to adjust the level a little bit higher to where you get at least that excursion. I'm getting that. I monitor the next frequency. I go to the next frequency point, maintaining this excursion level. So I'm constantly sweeping very slowly. And what's the frequency sweep? The sweep rates in MIL standard, you have a 3-second dwell at fixed points. But you can see you get all kinds of unique waveform appearances by these integration of this low frequency signal to a higher one. I continue to sweep the frequency, monitoring 3 things. So your eye is constantly going between things. Is the test article performing correctly? Do I have my peak-to-peak voltage that I should be going my test level, and am I not exceeding the forward power calibration in that voltmeter? So we're constantly monitoring all these activities. It's great if you have a partner monitoring the test article for you. So we kind of do this, and we keep doing the frequency test, shifting the frequencies until we get through all the frequencies. And this is a slow process. By the way, the generator here it was built for CS101 testing, and you can sweep a band of frequencies or all the bands and let it automatically go through it at the correct rate. Now, you need to verify that it is working right for the sweep rate. But we're constantly monitoring our activity on the oscilloscope, our test level, and EUT performance. We do this throughout the frequency range and determine if the UT passes, the test article passes or fails by that determination. I did want to point out a few things about the waveforms and etc. Ow! Remember, the oscilloscope is live. We intentionally put an oscillation transformer in place so the metallic connections that you have available are live. I didn't actually get shocked. I did want to remind everyone of this fact. With the testing complete, we've now recorded all the measurements, and we have a chart that we particularly like to use for presentation, where the blue line is the limit, and that's following the curve, and there's an applied voltage line which is nearly right on top of the blue line. So we're following just above the limit curve, and as you can see, when I get out into the areas where the slope is, I let the excursions exaggerate a little bit more. Also, we see some points here of susceptibility. I put those in just for demonstration purposes, but it's a measurement where the susceptibility frequencies occurred. The chart does not present adequate resolution for all the details, so you'll need to tabularize the data for reporting so the exact frequencies and exact levels are known. But this does provide a very good representation of the test. Thanks for joining me on this MIL Standard 461F test method review. I hope you find it helpful. I also hope you find the time to join us through the complete journey for MIL Standard 461F via the Espresso Engineering series. Thanks for watching.